All right, so we've got just a few more things to talk about before next week's test. A week from today is test number 2. I did want to mention, let's see, before we get into lessons for the day, there's some more assignments that are up. Oh, I didn't put, this is 6.1 and 6.2 homework. I'll label that a little bit better. But you've got the 5.5 lesson is what that is. It's like lesson homework kind of combined. That's due tonight. And then by Sunday, lessons on 6.1, 6.2, which we'll be talking about that material all today. Those will be due by Sunday. The homework associated with that is due on Tuesday. This is, as I said, it's 6.1 and 6.2 homework. Let me just fix that real quick. So it says what it is. There we go. All better. So that is due on Tuesday night next week. Our exam is going to be due on Thursday. I'm going to have a little bit more extra practice with the later section. I think it's all from 6.4 of chapter 6. Due on Wednesday night, but it's stuff that will it's all very similar. So it seems like we're not very much time to talk about chapter 6. The chapter 5 and chapter 6 are about polynomial and rational functions. A, rational functions are made up of polynomial functions, but B, the things we're talking about are the same concept. So once you learn how to just kind of adjust your thought process a little bit to like, what are you looking for? It's answering the same sorts of questions for both of them. And a lot of what we're talking about is really just the notation and interpretation. And so once you've done it for one sort of function, you can do it for a whole bunch of sorts of functions as long as you kind of know what to expect. So in any case, what I wanted to look at first today was one of the pieces of Investigation 5 from Module 5. Not all of this, but just some parts of it. We talked about on Tuesday, we talked about polynomial functions, and if you had a graph of them, you could figure out what the factors of them were based on seeing roots, and we could describe when they're increasing, decreasing, things like that, when they're positive or negative y values. But looking at this the other way around, let me just make this a little bigger. If I have a function f that's defined f of x equals x plus 1 times x minus 3 squared, kind of going the opposite direction from what we were doing in class on Tuesday. If I know what the factors are, I should be able to find the roots or the x-intercepts, horizontal intercepts of this, because this is a different format of it, like if we're thinking graphically, but if I had an equation, x plus 1 times x minus 3 squared equals 0, I can figure out when that equals 0 since it's already factored. They've done the hard part for things that are more than quadratic. Make it easier to use the zero product property. So in this case, for instance, x equals negative 1 or x equals positive 3 are the only two ways to make this expression equal to 0, because it can't like factor into some other entirely different thing. The unique factors of this are x plus 1 and x minus 3. Now, x minus 3 shows up there twice, but there's only two unique factors, so there's two distinct x-intercepts or roots of this function. So if I wanted to sketch a graph of it, which is would ask you to do like later down the page here if you have your own version of it, but I'll leave the function in view here. I know some things about this. I know that it's a polynomial. It's just powers of x. They're all multiplied together. It's not multiplied out right now, but that's okay. It would go through -1, just assume these dots are, or these hash marks are 1 unit. Go through -1 and positive 3 on the x-axis. And those are the only spots on the x-axis that it would hit. But notice also this is a, what degree polynomial would this be? What is the highest power of x that this would have? This be more than quadratic, right? If it was just x minus 3 squared, f of x equals, and forget this first part, that would be a parabola. But I've got an extra factor multiplied onto that, so without actually multiplying it out, I can still tell that this would be something with an x cubed. In fact, the first term is just x cubed, first term meaning highest power term. If I were to write it in that regular descending order of exponents, f of x, using kind of the shortcuts we talked about last time, the highest power term would come from multiplying together x and x and x plus 1, x minus 3, x minus 3, the highest power piece of each of those. And there'd be some other terms. The lowest power term comes from multiplying together the lowest power pieces of each of the 3 factors, positive 1, negative 3, and negative 3. So positive 1, negative 3, and negative 3 multiplies to positive 9. So this function is f of x equals x cubed plus some other stuff, and it ends with a plus 9, which in terms of the general shape of it, knowing that it has this x cubed, that tells me some things, general shape-wise. This plus 9 at the end tells me a specific point on the graph, because if this were all multiplied out, x cubed, x squared, x to the first power with whatever coefficients, this constant term, if x is equal to 0, would be the only part left. So 9 is the vertical intercept or y-intercept. If I sub in 0 for x, this is going to come out to be 9. 0, 9 is the point. So I've got a point at negative 1 on the x-axis, at positive 3 on the x-axis, and I'll just say that this is 9. 9 on the vertical axis, y-axis. So I know that. I also know that those are the only 2 points that I crossed or touched the x-axis. But x cubed graphs, we talked about these last time. If x is extremely large, all x cubed graphs kind of have the same pattern. If I have a positive x cubed, when x is extremely positive, this is extremely positive. When x is extremely negative, so is this. So the far right side of this graph is generally going up, and the far left side of the graph is generally going down. In terms of drawing a sketch of this, where I'd put my arrows right side up, left side down. I want to talk about some notation for that in just a minute, but putting together the rest of the pieces of this, I know I need to go through this point, and that point. And I can kind of play connect the dots to some extent. But keep in mind, I'm not allowed to go through the x-axis anymore. I have to go through this point also. So maybe I can say, all right, well, I'm going to go here. Got to go like that. And so you see at x equals 3, it's not a pass through the x-axis, it's a kind of bounce off the x-axis. If this x plus 1 factor weren't here, if it was just f of x equals x minus 3 squared, you would have had a parabola whose vertex is right there. X minus 3 squared would be a parabola with a vertex at 3, 0. And so this looks like that, right around x equals 3. If all I had was f of x equals x plus 1 without the x minus 3 squared, I would have a straight line, slope 1, that goes through 1 on the x-axis. Well, it would also go through negative 1 on the, or 1 on the y-axis. It will also go through here. Now there's some other things, but right around here, this would look just like y equals x plus 1. If I, zoom in close to both of those, they both look like that right around x equals negative 1. Y equals x minus 3 squared in this area looks just like that. But there's all these, there are other details and they're multiplied together. So in between and around, there's other things going on. So this is actually curved, it's not straight lines. But in terms of kind of imagining what a graph looks like without having to grab a graphing calculator or even make a table of values or anything, we can use a few key points, the roots the general shape of the overall graph or the general shape around the intercepts, as well as, maybe just this can kind of help. Knowing the constant term, getting a vertical intercept can help you kind of piece together how to connect the dots with the information we have. We end up with something that looks like this. Now, what I did want to talk about is a kind of more formal math way to say the right side goes up and the left side goes down, because that's kind of very informal. It's descriptive, but you're not going to see that written in college level math text. Instead of saying the right side goes up and the left side goes down, there's a couple of different ways we can write this. One's kind of sentence-based, but sounding a little bit more formal than goes up and goes down. And the other way is very notation-y. But I want to talk about both of them because both of them you'll see a lot. So if I want to talk about the right side goes up, what that means, what I'm talking about here is like there's an arrow that goes up and to the right. And it keeps going that direction. It doesn't go back down. There's no other turning around. But the larger x gets, the larger y gets. And so kind of sentence-wise, I could say as x, if I wanted to write it in all words, I could say increases. But what I'm going to write is slightly more notation-y and much faster to write. As x goes toward infinity, this was what, f of x? So instead of saying y, I'll say f of x goes towards infinity. So these are both positive. I didn't write the positive symbol on these infinities, but just like with other sorts of numbers, if there's not a negative sign, it means it's positive. This is about the right end. If I want to talk about the left end goes down. Well, left is when x is negative, and the more left I go, the more down I go. So as another sentence, I could say, as x goes to the left, as x approaches negative infinity. Now the arrow, when you're writing these sentences, we write left to right, and it's just kind of translating as x gets more and more negative. This is the translation of that, so we say the x part first. So when you're drawing it, you have to do arrow to the right, but it's just saying when x approaches negative infinity, or as x gets closer to negative infinity, or as x decreases without bound, you'll see that phrase. So does f of x, so does the y value. So this top sentence with symbols in it is the equivalent of when x gets bigger, y gets bigger, or the graph goes up and to the right end goes up. The bottom line here is the equivalent of as x gets smaller, y gets smaller, or the left end of the graph goes down. These are just more formal ways to say those things. Now, a more advanced way to say this, and that's also used for other purposes that we're going to use in chapter 6, is to make it less sentencey and just single notations. And the notation that we're going to use has, you'll see LIM, which is an abbreviation for limit. So what I'm writing is this first sentence here in another notation. And this is read, the limit as x approaches infinity for f of x is infinity. Now, infinity doesn't sound like a limit, it's unlimited by nature, but this means that, same thing, as x gets larger and larger, f of x is headed toward infinity. So the limit as x approaches infinity, when we're looking at function f of x, is infinity. And so this is normally just read quickly as the limit as x approaches infinity of f of x is infinity. But if you say it really fast, it's just a lot of infinities in this case. Similarly, statement 2 here, that we wrote kind of sentence-wise, as x approaches negative infinity, f of x approaches negative infinity. You say that kind of a similar way with this limit notation. The limit in f of x as x approaches negative infinity is negative infinity. So statement 1 above and below mean the same thing. Statement 2 above and below mean the same thing. They're two different, more formal math notations for things that you can describe just in your own words, like the left end goes down and the right end goes up. So it seems like, oh, that's a lot of excess notation. We use them for other things also, other than just end behavior, describing where the arrows go. We can talk about any point in a graph using the same notation. It doesn't have to be the end. It doesn't have to be x approaching infinity. It could be x approaching 2. When x approaches 2, y approaches, I don't know, whatever it looks like in that picture, 1. But normally we just say f of 2 equals 1 because the graph is going there. And those limit expressions are going to tell you about function values as long as the function doesn't have any weird gaps and jumps and stuff in it, which chapter 6 functions sometimes do. But in any case, a polynomial like that, we can analyze a lot of different pieces of it, the ends, the intercepts, x and y. We can talk about when it's increasing and decreasing, when it's positive and negative. The one last thing I wanted to talk about a little bit more, if you've looked at the lessons and the homework, you've seen this word in there before. It's a concavity. It's about the curvature of it. Is it curved upward or is it curved downward? Parabolas, like lines aren't curved at all. Parabolas are either curved up or curved down the whole way, right? This shape is called concave up, and this shape is called concave down. Rather than using, like, maybe familiar science terms, concave and convex, which indicate a specific perspective, this is just concave up and concave down, meaning like it's like a bowl facing up or a bowl facing down. This concave up can hold liquid, concave down cannot if you pour it from the top. So I do want to take a look at this particular function here. If I wanted to describe on that one where it's concave down and where it's concave up, when we talk about when the y values are positive versus negative, the dividing points were those roots. When we talked about when it's increasing versus decreasing, the dividing points were the tops and the bottoms of the hills. Like it goes up until we get to the top of the hill, then it goes down. Increases and then decreases. But when I'm talking about concave up and concave down, there's not a real easy to see spot in calculus. You'll learn how to determine algebraically where these spots are, where the curvature changes. But I know like this section to be concave up. This is like that parabola facing up, like x minus 3 squared. And I know since this seems to be at least the top of a hill, maybe it's not, I just kind of sketched this, but this part around here somewhere is going to be concave down. This is just a rough sketch from a few pieces of information, but it has to look something like this. So somewhere in between those 2 points, in between the maximum and the minimum, there's got to be kind of a changeover point. It's called an inflection point, but someplace in this graph, maybe it's around 1.5, I don't really know. Could look at a Desmos graph and maybe see more clearly, but I know calculus, I can figure it out algebraically, I don't really want to. We don't need to find it, just kind of generally describe. I know this is concave down. This isn't going to be wiggly and change back and forth. It's a pretty basic function. So it's going to be concave down to the left of that spot and concave up to the right of that spot. And you can see if you go to, here, let me just go to Desmos. Where's my, there we go. What was it? It was x minus 3 squared times x plus 1. Let me just zoom out the easy way. So this isn't precisely the top of the hill. The top of the hill is a little bit to the right of that. Also something you learn how to do in calculus. But you can see the general shape of the graph matches this. I don't have it zoomed precisely the same. But somewhere between this peak here and this valley here, there's got to be a changeover. So maybe it's, maybe, and there's not like a key point that Desmos is going to point out, like where is the point of inflection or where does the curvature change? But maybe it's around halfway between. There's no reason it has to be halfway. It's not like there's some magic symmetry of random functions. But let's say it's around, what did I say, 1.5 or something? This looks more like, yeah, that looks like 1.5, 1.6 or so. But I could say that the left part of the graph, negative infinity through positive 1.6 or so, that's curved down on that interval, left to right. Whereas it's concave up from 1.6 or wherever this is onward to the right. So from 1.6 to positive infinity, I can say that this graph looks to be concave up, just estimating wise. So in terms of how would I ever be able to estimate this well enough for iMath on a homework? It would probably, like multiple choice, which of these seems to be the interval where it's concave down. And it would be points that aren't like 1.5 versus 1.6, but does it change at this point? Does it change at that point? Does it change at, points that are clearly yes or no, that would be a change in the curvature. So in any case, back to where we were. So I just kind of use this to go over a bunch of things with polynomials and how to interpret what they might look like from their function rule, that is. Let's see. There's some of that. Nope, that's not the function I wanted. That's the messy part. Here we go. So this is toward the end. This question 8 asks to describe the end behavior of these. And you can see they're in an assortment of different orders, and for A and B, C's in factored form. But take a look at these 3 functions, A, B, and C. See if you can not just, what does it say to do here, even? Oh, this is just asking about end behavior. I do want you to state the end behavior using either this sentence type notation with infinities or negative infinities, or the limit type notation, either way, whichever you prefer. But for each of those 3, try to do that. And try to draw a sketch similarly, not by grabbing a graphing calculator or plugging in things, but just what you can tell, what you know, and some of them are harder than others, what you can tell about end behavior, if you can determine any roots. If you can't, don't worry about it, just say, it probably wiggles around and looks kind of like this. But if you know a vertical intercept, you should be able to find that. X-intercepts, if you can find them. And what the ends are doing. And then we'll take a look at these. So take a few minutes, take a look at those. End behavior you should be able to determine. Vertical intercepts, definitely. X-intercepts, maybe, maybe not, depends. But just, I might have mentioned this quite quickly. There's only a few options for what the ends of polynomials can do. And it's based on what kind of highest power they have. Odd highest power, like linear functions, cubic functions, fifth power functions, are going to have one end up and one end down. Just like, like lines, positive or negative slope. Just the middle is messier. Even powered functions, like parabolas, are going to kind of behave like parabolas. Both ends go the same direction. Is it up or down? And you can tell from the leading coefficient, because that one becomes dominant when the input variable, x in all of these, is extremely far from 0. it says here, if you do have a laptop on you, which I think everybody does, you can pop over, check this, and we'll see what the graphs look like, see if you're on the right track. Or grab a graphing calculator, let's use that. So, notice we have for A, we've got a cubic polynomial. For B, we have a 5th degree polynomial. Quintic, I guess, but nobody really cares about those names so much. And for part C, that would be a quadratic, 2nd degree. And it's not written out in, multiplied out form, it's in factored form, but factored form is useful for finding the roots, the x-intercepts. So if we're gonna think about those three. All right, well, for the first one, negative x cubed plus 4x squared minus 8. Just as a, this is useful in chapter 6 stuff too. F of x, yeah. Oops. Negative x squared plus 4x squared minus 8. When x is 0, 8's in charge here, negative 8, right? This is the only thing left, so this is 0, negative 8. But when x is large, these things take over, and the 8 becomes kind of unimportant. And in fact, when x is pretty large, it's really this term that becomes dominant. So when x is far from 0, I keep saying large, but I mean large in absolute value. Far away from 0, this graph looks like negative x cubed, more or less. And negative x cubed looks kind of like that, right? Regular x cubed goes through 0, 0, and the right end goes up and the left end goes down. Negative x cubed is the reciprocal of that, or not reciprocal of that, reflection of that, multiplied by negative 1. All the y values are opposites. When we're far from 0. When we're near 0, these other terms are kind of important, so it becomes a little bit messier, but generally speaking, the n's are going to have the same behavior as negative x cubed does. As x approaches infinity, as we go to the right, we're going down. This f of x, its values decrease. On the other hand, if I go to the left, or let x decrease, the y values increase. F of x becomes extremely large and positive. So end behavior statements, we could say it that way, or we could use those limit statements, either way. In the middle, it's kind of a mess, but that's what the ends are going to do. This graph would specifically have to go through 0, -8. It's a little hard to tell what else is going on because that's not anything that I know how to factor. If you know how to factor it, great, but I don't think it's factorable with integers. But if we just take a look at this, negative x cubed, if I can type today, there we go, minus 4x squared minus 8. Oh, it was plus 4x squared. So there's a lot of negatives in there. There we go. So zoom out a little bit. Left side goes up, right side goes down, it wiggles around in the middle a little bit, goes through -8 on the y-axis. If we were to zoom out a lot, actually what I want to do is zoom out in one direction. X-axis, there. If I just zoom out in one direction or one more than the other, because this is way too close to the y-axis otherwise, you can see that looks kind of just like regular x cubed from a distance. It's just when you zoom in and see the details when x is small, you can see what goes on. When x is not too far from 0, there's a lot of details. But when x is far from 0, generally what's happening is the same thing that happens with regular old y equals -x cubed. From a distance, those two graphs look pretty much the same. It's only when we get in closer that you can see that there's some differences in the middle. For instance, the green one is just y equals -x cubed. The first one we had has a section where it's concave up and another section where it's concave down. And there's a kind of switch over where it's decreasing, then increasing, then decreasing. Whereas the green graph has a section where it's kind of like half concave up, but it really just flattens out. It's not a very good bowl. And then it changes to concave down for sure, because this is curved downward like the right half of the bowl. But there's no increasing section to it. It just kind of decreases and then flattens out and decreases. Those extra terms in there make the middle a little bit wigglier, official math term. But it's only for a very small section when x is relatively close to 0. So, oops, this one. Looking at g of x, this one's going to go through the origin. I can tell because there's no constant number term. If x is 0, this works out to be 0. G of 0 is 0. But the leading term, dominant term here, is that highest power of x, x to the 5th. It's a positive 3x to the 5th, which would look pretty much like, then overall, if I were to graph g of x would look pretty much like 3x to the 5th if I'm looking at large values of x. Well, what does 3x to the 5th look like? Pretty much like 3x cubed. Not too much like 3x to the first power, because that's definitely a straight line, but same pattern, right side up, left side down, positive leading coefficient on an odd power, meaning that positive 3x to the 5th is definitely going to be the largest term in absolute value when x is far from 0. When x is positive, that's a positive term. When x is negative, that's a negative term. So I can say this like right side up, left side down, or for g of x, more this direction than the other direction. The right end goes up to infinity. When x decreases, so does g of x. Oops. So generally that sort of shape. From a distance, zoomed out, it looked more or less like that. What are the details of it? It goes through the origin, and kind of hard to tell otherwise. But let's see, 5x minus 4x cubed. And what was the last term? Oh, wait, 5x minus x to the fourth and 3x to the fifth. Which we said is pretty similar to just 3x to the fifth. In the middle, they're not so much the same. They both go through 0, 0. Unlike the last one, there's not even a constant term difference. But you can see, it's kind of a little bit goes up and down more, as opposed to just going kind of straight across. But if you zoom out, generally the same pattern. They look very similar. So when x increases without bound or decreases without bound, g of x and 3x to the fifth have approximately the same values. They're very similar. They have the same pattern. So if I wanted to know about the x-intercepts, 3x to the fifth only goes through 0, 0. This one seems to go through a couple other points, but I don't really know what they are. 1 point something and negative 1 point something. Not symmetric number, not the same positive and negative number. Just a couple of numbers, 1 point something. But analysis-wise, I could talk about where it's concave up, concave down, where it's positive and negative by approximating from the graph. The last graph, however, or the last function on here, negative 2 times x plus 1 times x minus 3, that's a low enough degree and it's factored. We should be able to say anything we want about that one. That's definitely a parabola. Does it open up or down? H of x equals negative 2 times x plus 1 times x minus 3. Is it a concave up parabola or a concave down parabola? Down, yeah. That negative 2 gives it away. If I were to multiply this whole thing out, I'd have a negative 2 times x as the first term, negative 2x squared. And the last term would be negative 2 times 1 times negative 3, whatever that is, 6. I almost said 7. 6 is the last term, so it would be a negative 2x squared plus something plus 6. So whatever else that means, opens down, goes through 6 on the y-axis, and we know where the x-intercepts are, because it's parabola in factored form. So no fancy work on this one. But if we wanted to graph it, we've got x-intercepts at negative 1 and at 3. So the vertex would have to be someplace at x equals 1, halfway in between, because they are symmetric. It's a very specific shape. And I know this goes through 0, 6, because it has that plus 6 as the constant term, but that's not the top. It goes up and then back down. Both ends are down. So we're writing limit statements about this function h of x. Both ends go down. H of x approaches negative infinity, regardless of whether we're talking about x increasing or decreasing without bound. But if I wanted to know where the vertex is, I could use the symmetry of this shape to figure it out. It's got to be halfway between the x-intercepts. The vertex is at 1 comma something. And I have a function for it. So I could figure out 1 comma what, just with a plug in 1. So I'd have negative 2 times negative 2. It should be an 8. So a vertex is a key point in a parabola. Other shapes don't have that sort of thing. There's not like a key point in a random cubic polynomial that's definitely going to be the top of a hill or something. You've got to do more work to get those. But with parabolas, They're fairly basic, kind of like lines. There's only a couple things to know about lines, a slope and an intercept, and then you're done. That's the whole thing. There's only one way it could look. With a parabola, you need to have a little bit more information to know precisely what parabola if you don't have the whole function given to you, but they are symmetric. So if you have some pieces, you can find out some others just from symmetry. Especially if you have both roots, you know where the vertex must be, left to right wise, x wise, input value wise, and you can figure out the rest from there. So just some, I don't know, kind of common sense or figuring about these. There's a lot of questions you maybe have seen in the homework where it describes a whole bunch of things in sentences, and there's a homework question I know about throwing a rock from an 80-foot cliff, and it goes up and it hits the ground at a certain point in time, and there's a formula you're supposed to be able to write from that using its intercepts. It really helps if you have long sentences with a bunch of numbers for these coordinate pairs. I would highly suggest drawing a sketch, even if it doesn't say anything about draw a sketch to help with this. For that particular homework question, I'm just going to create some it wasn't dropped from a cliff, it was thrown upward from a cliff, but it was thrown from like 80 feet, and it went up, and then it went back down and hit the water. And we had some information like, it started at 80 feet at time 0, so this is time in seconds, and the height in feet. So let's say that it started time 0 at, I'm just going to make up some numbers. This isn't precisely what was in the problem. Let's say it started at 80 feet, it was thrown up, it hit a maximum height of 120 feet at time 2. I'm just going to pick nice round numbers. So, okay, 2, 120. That was the maximum height it hit. And then it hit the ground at some particular point in time. And I'm going to make up a number that probably won't quite follow physics, but I'm just going to make up some number here. Let's say it hit the ground then at time, excuse me, 4.5. And just wanted to know, so sorry, this is not quite to scale. My 0 to 2 looks larger than my 2 to 4.5 is, but we have numbers, so we can imagine. It was a quadratic function. It said something like, write a function in the form y equals, I think it was c was the letter used, times t minus t1, t minus t2, where t1 and t2 represent the roots of the equation. So we have one of those. We have a vertical intercept and we have a vertex. We don't have both roots. And this c number is kind of a mystery. So if I wanted to be able to solve this, I have pieces. It's kind of like we can use the symmetry of the parabola, and we can also use points that we have. Kind of like if you have a straight line and you're given a couple of points and asked to write an equation. You can use the couple of points to find the slope, and then you can find the y-intercept by plugging in some point and figuring out what it has to be to make the equation come out right. That's finding b in that situation is kind of like a finding c here. So I know I've got a 0 or a root at 4.5, 4.5 comma 0. So I can put a 4.5 in either of those spots. It doesn't really matter which. I can figure out where the other root of the equation would be, even though it doesn't really make any sense in terms of throwing a rock. It would be at like negative time sometime, because the other root would have to be to the left of that starting point, because that starting point was up too high. So someplace over there, but I can figure out where it is because of symmetry. Now, this is where my not quite to scale, causes a little bit of problems. So I'm going to make this look a little bit better. There we go. Now it doesn't look quite so lopsided. But the vertex out to one intercept is 2.5 units. Therefore, the vertex back to the other intercept also has to be 2.5 units. So the x value at this location must be -1/2, -0.5. That way the vertex is in the middle of the two intercepts. It's supposed to be a parabola because of this function structure there. So this has to be halfway between. If it's 2.5 units to one intercept from the vertex, then it's 2.5 units left to right to the other one. And so in order to write this function, let's kind of jump this over here. It's t's instead of x's, but I have a -0.5 and a +4.5 as my roots. So that's t plus 0.5 and t minus 4.5 as the corresponding factors. And so my function y equals, or whatever you want to call it, h of t, the height at time t, is some mystery number times these two factors. This is the only other thing in here that's supposed to be a number. This is kind of like you're trying to write the equation of the line and you're at the stage where you have like y equals 4x plus b. You're supposed to have a number for b, but in your final answer, the y and x are going to be there. In our final answer here, the t and the y are going to be there. But that c is supposed to be a number. And I can figure out what number it's supposed to be by using, well, if I put in 2, 120, I can do that. This is going to be easier, 0, 80, because subbing in 0 is usually pretty simple. But I can sub in either of these other 2 points. I don't want to use these intercepts, because if I do that, if I sub in either of the t values, 4.5 or -0.5, this whole side's going to turn into 0, and that'll make it equal 0, and I can't find c. But I can either use that vertical intercept or the vertex as a, well, it's not xy, a ty point to sub in for t and y so that I can find c. And like I said, subbing in 0 is usually pretty easy, so if I sub in 0 for t, I'm supposed to get 80 for y, and I'll figure out what c is. But subbing in 0 for t gives me 0.5 times -4.5 times c, which is what, -2.25? Times c is supposed to equal 80. So I can divide and get a negative number for c, which should make sense. Its parabola opens down. I don't know what 80 divided by -2.25 is off the top of my head, but it should come out not too badly. Let's see, what is 80 divided by 35.5 repeating. So, where am I going to write this? I'll just write it over here. Find little tiny pieces of chalk. I'll just put -35.5 approximately. Just like I said, I was making up an equation that doesn't quite follow physics. But in any case, that's the strategy for solving for those. You can use the symmetry and then plug in a point that you know that'll allow you to solve for a missing constant. So it's kind of a parabola equivalent of, and then sub in an xy point to solve for b. All right, so that's all I want to say about polynomials. That's kind of the messiest sort of problem that we dealt with in this chapter. A lot of it's just kind of looking and analyzing what's the pattern. So that's kind of where I want to start with chapter 6, rational functions, which rational functions are ratios, and they're not just ratios of anything, they're ratios of polynomials. So if you know how polynomials work, then ratios of polynomials, we can look at those also. Let me go back to here. Actually, open up a lesson on this one. The 6.1 lesson is something that you're going to have due by Sunday, but just it has a little introductory paragraph in this. So rational functions. 6.1, there we go. It's just about how to look at them. They look messy because they're fractions, but here, I want to zoom in properly. There we go. So a rational function is a function with output values that tell us relative size of two polynomials. For example, f of x equals 4x plus 10 over x squared minus 5x plus 1 is talking about the relative sizes of that linear function in the numerator and the quadratic function in the denominator. So thinking about what sorts of values this has, it's going to tell you how much, like how many times larger one is than the other by looking at the size of this. I think that the bottom is a quadratic function. Quadratic functions get steeper and steeper as you go on, whether it's positive or negative steepness. This line on the top, 4x plus 10, it goes up, it increases at a constant rate of 4 y units per x unit. So I know that the denominator is growing faster than the numerator when x gets large, because when x is increasing, both of these are going up. One's going up in a straight line and one's going up parabola style. The parabola is growing faster. So if I'm thinking about, well, what sort of values does this f of x have? Well, the denominator is getting larger faster than the numerator is. Its value is probably going to overtake the numerator really quickly, even though it starts out when x is 0, the numerator is 10 and the denominator is 1. It's a 10 to 1 ratio. But by the time x is like 5, oh wait, actually at x equals 5, it's gonna the denominator is still 1. Let's say when x is 10, the numerator would be 40 plus 10, 50, and the denominator would be 51, 100 minus 50 plus 1. So by the time we're at x equals 10, the denominator's overtaken the numerator, it's larger, and since it's a parabola, at this point we must be past the vertex since it's grown. So it's going to be growing faster eventually than the line is. It's overtaken it already, so it's going to keep going up faster than that, and the value of this then was originally 10, just table of values wise. I'm looking at what is this called? F. X, f of x. When x was 0, we had 10 over 1. So just 10. By the time we got to x equals 10, we had 50 over 51, which is just slightly less than 1, 0.9 something. If x were 100, the numerator would be 410. The denominator should be a lot larger than 410, because I'd have 100 squared, which is, what is that, 10,000, minus 500 plus 1. So 9950, 1. If I'm subtracting correctly. In any case, that denominator is a whole lot larger than the numerator. And as x gets larger, that denominator, relatively speaking, is going to be getting larger more and more quickly, or more importantly, it's going to be increasing faster than the numerator is. So these numbers, the numerator and denominator, would both be larger and larger numbers as they plug in larger and larger numbers for x. But the bottom compared to the top is going to be very, very large. This is approximately 1. 400 over about 10,000, what is that, like about 0.04? It's pretty small. And I'm not going to get any negative numbers, but the denominator of this is going to get larger and larger. So the pattern-wise, I'm going to get a fraction that gets closer and closer to 0, although remains positive, as x gets larger and larger. Question?
Do you think you could example B on the first question?
Yeah, so just down here?
Yeah.
All right, yeah. So these questions are about domain. So we'll get to that in just a second. I just wanted to talk about the sizes of them, but yes, we'll get back to there's issues with these. Specifically, this first example here, not very easy to see, but if you make a fraction, you can't have denominators of 0. This is a quadratic function. It very likely has some y values that are below 0. I didn't pick anything between 0 and 10, but other than briefly, when I picked 5, I'm like, oh, well, when x is 5, this is 25 minus 25 plus 1. Same as it was at 0. So if I pick anything between 0 and 5, this is going to be something negative. And somewhere between where it's negative and where it has values of 1, there's unpleasant numbers, wherever you'd have to use quadratic formula to find this, but you could find places where that denominator is 0. And obviously we want to avoid that. This isn't an example of one where I want to work on finding out where precisely it's 0, but these rational functions have issues that polynomials separately don't, because they are made into a ratio. So if we're talking about where it makes sense to compute this ratio, well, it wouldn't make sense to compute the ratio when the bottom one, the denominator polynomial, has a value of 0. So things like, in this example 1, let me make this bigger again. F of x is 8 over x. Not a very interesting polynomial on either the top or the bottom, but it is a 0 degree or a constant divided by a first degree linear. Well, it's not polynomial, I guess it is, but monomial, single term expressions. But if x were 0 here, that wouldn't have a value. There's no way to compare the size of 8 and the size of 0 in terms of one is 4 times as big as the other, because 8 isn't any number of times bigger than 0. 0 can't be multiplied into anything else. So 0 as a value for x doesn't make sense here. So the domain of this expression has to exclude x equals 0. Similarly, for part b, the domain for this function in part b, 2x squared over x minus 8, has to exclude the possibility of x equaling 8. And in part c, because of this, it's two linear functions, which linear functions, oh, that's easy. Well, the quotient of two linear functions is still a weird pattern, but the thing to remember is we shouldn't consider whenever that denominator is 0, which would be at x equals -4. Any other value for these three are valid parts of the domain. This question was specifically asking not just what is the domain, it was asking what's the value. And f of 0 in this first function, if I sub that in, I get 8 divided by 0. I can't do that. So it said enter DNE for does not exist, which is a fairly common math abbreviation. Same thing here. If I try to evaluate this at 8, that value doesn't exist. It'd be 128 over 0. Or this one, however, +4, that's perfectly fine. It's not a nice number, it's just 7/8. But 7/8 is a number, it's not a division by 0. So 0 as the denominator of a fraction is not a good thing to have. It doesn't have a known value. We can't talk about that ratio. But all that means is our domain for the function that gave us that is going to exclude those sorts of input values, x values in these cases, that cause a denominator of 0. So in red here, it says that the domain of f, being this rational function here, the domain of a rational function includes all real number values of x except for ones that make the denominator polynomial equal to 0, the roots of the denominator polynomial. So in this one, they called that denominator h. Sometimes you'll see it listed as d for like n of x and d of x, numerator and denominator. Sometimes you'll use p and q, polynomial and another polynomial using a different letter because q is next in the alphabet. But again, rational functions aren't just any old things put into a fraction. It's specifically a polynomial over a polynomial, including potentially monomials, single termers, but it has to be constants, first powers, second powers, third powers, etc., of some variable. Not logarithms, not 3 to the x exponential expressions, not negative exponents, not square roots of variables. So if you're looking for domain, the domain excludes these individual numbers, which means weird stuff happens in those functions because there's just an individual number that's bad and everything else is okay. But let's see. Here we go. I want to take a look at, not those. Exploring ratios. So it says let f of x equal 5 over x. And we're going to take a look at what happens as, and there's some weird notation here. I just have x approaches 0, but then there's one with a plus and a minus. This doesn't mean that 0 can be positive or negative suddenly. There's not new rules for math. These little, it's like in an exponent position, but it's a positive or a negative sign. That's indicating some place we're looking around 0. So x is approaching 0. We talked about only x approaching infinity or negative infinity before. If you're approaching infinity, we know where you're coming from, things smaller than infinity, because there aren't any things bigger. If you're approaching 0, you could be coming at it from either side. And that's what the little plus and the minus are for. In this sort of notation, x approaches 0 with a plus means you're going towards 0, but starting with things that are a little more than 0, 0 plus a little bit. So going towards 0 from the right. And why that's important to think about, this was, let's see, 5 over x was the function that I have. You might have something slightly different. But let me go back to Desmos for a second and graph. Let's see, y equals 5 over x, which looks like this. I'm going to zoom out a little bit. So if I ask you what's going on with this function as x approaches 0, you're like, well, it's gone crazy. There's a big gap in the graph, and x equals 0 isn't allowed. That would be a vertical asymptote, is the name for what happens there. It's a divider between two sections of the domain. There's no value at that spot, and there's something going on to the left and to the right of there in this case, but it's two completely different things. It could be okay if maybe in a different graph, maybe this is up there, something like 5 over x squared would have all positive values. But if I want to describe what's going on in this graph, we could talk about the end behavior just like we did for polynomials. Looking at the graph, I can say, oh, as x approaches infinity, y approaches, oh, it looks like 0, kind of like the one that I just erased, where the denominator is getting larger faster than the numerator, which would make sense because this was 5 over x. The numerator isn't doing anything. This is called f of x. So if I think about what happens as x approaches infinity, well, 5 over 5, 5 over 10, 5 over 100, 5 over 1,000, 5 over a million, 5 over a billion. Those are always going to be positive numbers, but they're getting smaller and smaller because the denominator's expanding so quickly and the numerator isn't actually changing at all. It's not even growing slower, it's just not growing. So I could say for this, as x approaches infinity, f of x, it's not ends up or ends down. Rational functions have this other option of they go out along a specific y value. In this case, it's 0. Because I know these ends are getting closer and closer to 0 as this denominator gets larger and larger. It's never going to become 0 or negative, but it's shrinking and it's staying positive. So it's getting closer and closer to 0. If I were talking about the left side, same thing happens. If I put in a negative value for x, 5 over negative 10, 5 over negative 100, 5 over negative a million, 5 over negative a billion, it's going to be negative all along, but that negative value is going to be like negative 0.00001, so just hardly below 0. So I'm going to save myself writing and say as x approaches either positive or negative infinity, f of x, the y values, approach 0. They flatten out, graphically, it looks like they're right along the x-axis. So that's what's happening at the ends of the graph. If I want to talk about what's going on in the middle of the graph, because it's a mess, I know that there's y values for every single x value I can imagine, except for x equals 0. But if I want to describe what those x values are like, say, well, the ones just to the right of the x-axis, as long as x is positive, I've got positive values, right? 5 over anything positive is positive. If I put 5 over 1, 5 over a half, 5 over, like if I'm using positive numbers, but these positive numbers are getting closer to 0, I'm going to have extremely large positive numbers. So like 5 divided by a half is the same as 5 times 2. 5 divided by 0.01, 5 divided by 1/100th is 500. As I get closer and closer to 0 with my x values, if those x values are positive still, a little bit to the right of 0, I'm going to get extremely large positive numbers for this. Small denominator makes a big fraction, right? And that's what this example is looking at 5 over x. If I look at x approaching 0 from the right, if I put in 0.5, 5 over 0.5 is 10. 5 over 0.1, 5 divided by 1/10, is 50. 5 divided by 1/100th is 5 times 100, and so on, and so on. So the closer x gets to 0, but staying to the right of it, keeping positive numbers. As x approaches 0, but is more than 0, x approaches 0 with that little plus, that's usually right. As x approaches 0 from the right, but if that's confusing, because approaches 0 from the right, okay, start to the right of 0 and then you go left. That's what this is. These sets of x values, this sequence of numbers is approaching 0, but is staying to the right of 0. They're all to the right of 0, but they're approaching 0 as they go down the sequence. My y values in sequence are getting larger and larger without bound. So notation-wise, and I'm out of chalk that I can hold on to, if I talk about x approaching 0 from the right, f of x gets larger and larger. Or in the graph that we had, this one, if I'm to the right of 0, but approaching 0, zoom, way up. F of x approaches positive infinity. On the other hand, if I approach 0, but am to the left of 0, approach 0 from the left, or use values that are 0 minus a little bit, that's talking about, there we go. Oh, sorry. If I were to use this option instead, I'd have to have numbers in here for x that are all negatives. I thought it was going to switch for me, but it doesn't. But if I change from positive 0.5 to negative 0.5, that just changes this by a factor of -1. 5 over negative 0.5 is -10. 5 over negative 0.1 is -50, -500, -5,000, -50,000, etc. That's talking about as my x values get closer and closer to 0 but remain to the left of 0, my y values, because that's 5 divided by this negative number extremely close to 0, gives us a negative result, and it gets more and more negative. So I can say as x approaches 0 from the right, the function goes to infinity. Or to the right of that gap in the domain, the y values are extremely large and positive. To the left of that gap in the domain, to the left of 0, my y values are extremely negative. And so when we have these weird splits in our graph, because we can't connect the two pieces, if you connected them, there'd have to be a point where x was 0, and x equals 0 doesn't make any sense when we've got 5 over x. So there's just two separate pieces to the graph. And lots of times when people are sketching these by hand, they'll draw like a dotted line to help you line it up. There's not like a dotted line that's part of this graph, but that dotted line that you might see like drawn along where the y-axis is to demonstrate this is where the graph doesn't exist. There's stuff to the left and right. Here's a dividing point that kind of is helpful when you're sketching things manually to keep your graph from accidentally crossing it or help somebody else see what you were trying to graph. But in a computerized graph, you're not going to see any like dotted lines show up here to indicate those disallowed points. The blue is where the graph exists and nothing happens. It's not like it's off the screen. It's just there's no value when x is 0. So let's see. Here we go. I thought there was another one here. But here's the other half to that. If I'm looking at x approaching 0, but using values that are all to the left of 0, that's what this is. X approaches 0, so going through this sequence of numbers, which is getting closer and closer to 0, but they're all left of 0, this is where we'd get things like -10, -50, -500, etc., which this sequence of y values is decreasing without bound. So we just demonstrated that as x approaches 0 from the left, f of x is headed towards -infinity. So again, there's another notation for all of that, which is a little bit messy, writing this out in sentences. And so I'm going to write all of this using that limit notation. The end behavior is talking about when x is far from 0. And so I could say the limit as x approaches either positive or negative infinity for f of x is 0. The ends of this graph are headed towards the y-axis. They have y values extremely close to 0 on both ends. If I want to talk about what's happening near the vertical intercept, or the vertical asymptote rather, as x approaches 0, which 0 is just 0, it doesn't have a positive or negative sign. From the left, we're going down. If I approach 0 plus, approaching 0 from the right side of 0, but near 0, the graph is going up. So I'll just put the positive there to emphasize that, but to the right of 0, we've got values that are headed towards positive infinity. The closer to 0 we get, but stay to the right, the y values are near positive infinity or increasing without bound. As we approach 0 but stay to the left of 0, the y values are decreasing without bound or going towards -infinity. All right, so that's some asymptotes and domain and end behavior and limit notation for today. I hope that helps get through the notational aspects of these. There's some computation. You're going to be asked to find some function values and look at the pattern, but you should be set to do anything up through the 6.1, 6.2 homework. Just got a few more details. We'll wrap up with end of the chapter sort of stuff and then exam review on Tuesday next week. So I will see you then.